Hi, this is Dr. Goldstein, and I am going to discuss continuity of piecewise-defined functions. We are going to take a fairly detailed look at this one example. So this is f of x equals 4 minus x when x is less than or equal to 1, and x minus 1 when x is greater than 1. And our question is, where is f of x continuous and discontinuous? Okay, so to look at this, first we realize that the two parts of this function, 4 minus x and x minus 1, these are linear functions. Just meaning that they have the form mx plus b. And so we know that they're continuous everywhere. So these are continuous everywhere. So the only place where this function could be discontinuous is where those two parts come together. So f of x may be discontinuous at x equals 1, where the two parts come together. So that's what we need to check, whether or not f of x is continuous at x equals 1. And just as a reminder, the definition of continuous that we are working with is that f is continuous at the point x equals c if, when we take the limit as x goes to c of f of x, we get the value of our function. So that is the definition that we're working with. That is the condition that we need to check about this function. Okay, so in order to compute this limit as x goes to 1, we have to compute the left limit and the right limit separately because our function is defined differently on either sides of that. So a quick reminder, when we're taking the limit as x goes to not to 0, x goes to 1 of f of x, this means that x is in this interval 1 minus delta comma 1 union 1, 1 plus delta. And so what we have is on this part of the interval over here, x is less than 1, and on this part of the interval over here, x is greater than 1. And so that is why we need to use the left and the right limits, because in the left limit, we are just talking about x being in this left part of that interval, if you remember from the definition. And in the right limit, we are just talking about x being in this right part of that interval. So these two we can compute because we know what our function is to the left and to the right. Specifically, to the left, we can take the left limit and we can use 4 minus x because we know that f of x is equal to 4 minus x when x is less than or equal to 1. And that's what we're talking about. We're talking about 4 minus x when x is less than 1. And so now we can just plug that in because we know that 4 minus x, whenever x is less than 1, which is what we're talking about, 4 minus x is continuous. So we can just plug that in. So we have 4 minus 1, and so we have 3. So again, the idea here is in the left limit, we only have x less than 1. So the left limit uses values of x that are less than 1, so we plug into 4 minus x. Okay, for the right-hand limit, we know that f of x is equal to x minus 1 when x is greater than 1, and that's what we're talking about when we come from the right of 1. And so we are taking the limit as x goes to 1 from above of x minus 1. So again, any number that I plug in that's bigger than 1, I'm using this part of my function, and so I just plug that in, and I get 0. So again, the idea is that the right limit uses values of x that are greater than 1, so we plug in to x minus 1. Okay, so overall, we have these two limits. We have the left limit is equal to 3, and the right limit is equal to 1. What did I say? The right limit is equal to 0. And so overall, the two-sided limit, the limit as x goes to 1 of f of x, does not exist, because the left and right limits are not equal. This is one situation where left and right limits become very, very, very important when you're dealing with a piecewise function, and they're important precisely at that point where the two parts of the function come together. That's sometimes called a break point. So the answer to our question, is the function continuous at x equals 1? We know that no, f of x is not continuous at x equals 1 because the limit does not exist. And that means that it cannot be equal to the value of the function. Okay, so that answers our original question. But because we know that this function is not continuous at that point, we could ask, is our function either left or right continuous at that point? So again, just so that we're on the same page, left continuous means that the left limit, the limit as x goes to c from below of f of x, is equal to f of c. And right continuous means that the right limit, the limit as x goes to c from above of f of x, is equal to f of c. So again, we computed on the last slide that the left limit is 3 and the right limit is 0. And if we actually look at the value of the function at 1, well, the equals part in the function is on the top part. So again, we're going to use the 4 minus x part for x equals 1. And so f of 1 is 3. This is equal to the left limit. This is equal to the limit as x goes to 1 from below of f of x. So f of x is left continuous at x equals 1. And we notice that f of 1 is not equal to the right limit. It's not equal to the limit as x goes to 1 from above of f of x, because we computed that that was 0. So f of x is not right continuous at x equals 1. Okay, cool. So we can ask ourselves what kind of discontinuity this function has. So here's a new question. What kind of discontinuity is this? And the way to answer this is to think, well, my function is smooth, and I don't have any breaks or jumps, and it hits 3, and then all of a sudden it jumps to 0. So I have a jump discontinuity. So a jump discontinuity is where the right and left limits are not equal. Okay, so let's sum up this example by looking at the graph of this function. So again, there's my function, and this is what it looks like. I have the left-hand part of this graph is the graph of 4 minus x, and that goes up to x equals 1 and includes it because that's where the equal sign is. And then the right part of this function is the line x minus 1, and that just starts at 1 but does not include 1 and goes on from there. So visually you can see that you have a jump, and overall you can see that this function is continuous on the interval from minus infinity to 1, including 1, which this bracket here means that it's left continuous at x equals 1. And we know that our function is continuous on the interval from 1 all the way up to infinity. And the parentheses here means that it's not right continuous at x equals 1. And that's kind of nice because that corresponds to the way that we draw this with the closed dot and the open dot. So this is how we describe continuity of piecewise-defined functions. We have to look at each part of the function to determine whether or not they're continuous, but then the main thing that we have to look at is this breakpoint, which in this case is x equals 1, and it's this place where the two parts of the function come together. So the breakpoint of x equals 1 is where we have to check. For discontinuity. All right, so I know that piecewise functions can be very confusing for people, so I hope that this helps in understanding how to take limits of piecewise-defined functions.